All right, this is Notes, Chapter 2, Section 3, the basics of functions. So we're going to be going into functions and doing a lot with functions. So any set of ordered pairs is called a relation. Like we saw with the linear regression, there was a relationship between our two variables. And if there was a positive or a negative relationship between them, we could find the line of best fit. And that was for a linear function. But really, any set of ordered pairs is called a relation. They're related somehow. The set of all first components of the ordered pairs, which would be which values? Set of all first components, that will be our x values, is called the domain. All right, again, this is my x values. All right, and the set of all second components, the set, second components, is called the range. And of course, in our ordered pairs, those are our y values. All right, this should be a review for you because you've seen domain and range with ordered pairs, definitely in Algebra 2, for sure. And I'm not quite sure if you see it in Algebra 1 or not, but you should be somewhat familiar with this already, that the domain and the range, well, we did this with circles. We found the domain and the range of the circles. All right, so here is a set of ordered pairs. I know it's a set because I see the set notation, and I know they're ordered pairs because I see the parentheses. Okay, so this is a relation. So, excuse me, when you are asked to give the domain and the range of the relation, we're going to do D for domain, R for range. It is a set of values. And you're going to just list the x values, not in parentheses. We're just going to list the x values. So I see here 5, 10, 15, 20, 25. Those are my x's. None of them are repeated. Remember, if they are repeated, you list them only one time. But none of them are repeated. So I've got a 5 and a 10 and a 15 and a 20 and a 25. Okay, that's my elements of the domain of this relation. The range, we're going to do the same thing. It's the y's. 12.8, 16.2, 18.9, 20.7, 21.8. None of them are repeated, so I must list them all. 12.8, 16.2, 18.9, 20.7, and 21.8. Okay, that's my domain and my range of the relation. I'm going to put as a little side note here, list each element once. Only. Even if it occurs 3 times, you list it 1 time. We don't need to have it in the set of the domain or the range if it's listed more than 1 time. All right. Let's talk about definition of a relation. Okay. Well, we're going to put the fill-in word right here. Definition. A relation in which each member of the domain corresponds exactly to one member of the range is called a function. Okay, so each member of the domain corresponds exactly to one and only one member of the range is called a function. Now, because I like how I have this written out on paper, and it's already done in colors, I'm going to project this onto the screen and explain it to you. So you can pause the video and get this copied. But I would probably do that only after I explain it. Okay? So try to zoom in a little bit more here for, oh, too much. One more. All right. So I have this relation that I want to illustrate here in the notes. Okay. So I've done this twice. All right. Let me just talk about this one over here. My relation is autographed CDs, compact discs, music, and friends. So people that I know, my friends. Could be family, doesn't really matter. So in my set of ordered pairs, which is called a relation, I've got A, 1, B, 2, C, 3, D, 2. And so why did I list that way? Well, here, this is called a mapping diagram, okay? And so typically in a mapping diagram, you'll see these ovals and you'll have values inside the ovals. And so I'm going to put all the elements of my domain into the first oval. So my domain, if you look here, A, B, C, and D, right? It's the X values in the ordered pairs. And then what's my range? 1, 2, and 3. Because notice, I've got a 1 here, a 2 here, a 3 here, and this 2 is repeated. I only have to list it once. You just list it one time. All right, so I map. I'm like, okay, A goes to 1 because it's paired with 1 in the ordered pair. B goes to 2 for the same reason. C with 3, D with 2. All right, that's my mapping diagram. And I'm saying that this first relation is a function because I can give 2 different CDs to the same friend. That's something that would work. And when something works, we say it functions. Okay? So I could give 2 different CDs to the same friend. I mean, maybe the other friends will get upset because I gave one of my friends 2 and only gave them each 1. Yada, yada. Wow, big deal. So what? They're just going to have to get over it, right? But this is something that I can do. This is something that can happen. All right? And so if we look at the ordered pairs and or the mapping diagram, you should see here that all X values must be different. The Y values can be repeated, okay? But each X has to go to 1 and only 1 Y. In other words, I cannot have the same X value going to 2 different Y's, right? Function is 1 to 1, each X for each Y. I cannot have the same X going to 2 different Y's. Okay, over here on this side of the relation. So I kind of switched it up. I still left the relation be autographed CDs and friends. And I still have a set of ordered pairs where I labeled my CDs, my compact discs, A, B, and C. And this time I have 4 friends. And if you look in the mapping, you know, A goes to 1, B goes to 3, C goes to 2, and B goes to 4. See, I have the same X being paired with 2 different things. And when I think of this in terms of something like giving away autographed CDs, and someone had once said to me, what if you make a copy of it? I'm like, well, you can't really make a copy of an autographed CD. You can make a copy of the music on the CD, but you can't make a copy of the autographed CD. Those are originals. Okay, and so if you think about this logically, I cannot give the same CD to 2 different friends at the same time. They can't both claim ownership of it in different homes. Okay, so this is something that would not work. This is not a function. Okay, and this is a pretty basic example of how to break down your domain and your range and to find if a relation is a function or not. But bottom line is, if the X's are repeated, this thing is not a function. The Y is okay, but not the X's. You know, I give another analogy in some of my other, in my Algebra 2, like my Honors Algebra 2 class, that, you know, I have this set of ordered pairs. So this would be like X1, Y1, X2, Y2, X3, Y3. Okay, just for lack of a better, and I'm running out of paper, I've got these ordered pairs, X, Y, and X's and Y's, right? X1, Y1. X2, Y2, X3, Y3. And I give the analogy of going to the prom. I know, this is going to sound weird. Now, biology tells us that females have 2 X chromosomes, yes? And biology tells us that males have an X and a Y chromosome, right? And so, mom can only pass an X chromosome, when the egg is fertilized. I know we're going into like a biology and a fertility lesson here, but hey, whatever it takes, okay? So females have 2 X chromosomes, males have 1 X and 1 Y. Now, if mom can only pass an X chromosome to the baby, dad, though, can either pass an X chromosome or a Y. So if dad passes an X, like mom can only pass an X chromosome. If dad passes the X, then this is a girl baby. But, again, mom can only pass an X. She doesn't have a Y to give on. But if dad passes the Y, then we have a boy baby. Okay? So why do I give that analogy? What does this have to do with anything? Well, I give the analogy because in my algebra land, I say that X is a girl and Y is a boy. And it's for this very reason, okay? So this is a girl and this is a boy. This is a girl and this is a boy. This is a girl, this is a boy. Okay, and this is just one of my crazy analogies. So here I've got a couple going to the prom. Here I have another couple going to the prom. Here I have another couple going to the prom. Now, look, each X is different, right? This is X1, this is X2, this is X3. And that's fine. The Ys, maybe, maybe the Ys, and where I'm going with this is attire for the prom, okay? So, if, let's do this. If this girl has dress A on, and this guy has tuxedo A on, that's fine. That'll work. And if this girl coming to the prom has dress B on, and this guy has the same tux on as this, maybe something's a little bit different. Maybe the color of the cummerbund or something. I don't know. And if this girl comes to the prom and also has dress A on, but, this guy has a different tuxedo on, this is something that's not a function. Notice, the X's are the same. Folks, we know that the girls don't want to come to the prom with the same dress. This is something that would not function. However, the guys, they don't really care. So we can have the Y values being repeated in a function, just never the X. This thing, not a function. So, take the analogy for what it's worth. If it helps you to remember, like, oh, yeah, it's the X's because the X is the girl and the prom dress thing, okay? Then let that help you know what you're looking for to tell if a relation is a function or if it's not a function. Okay, enough of that crazy idea. If you have not copied this, then you may, at this point, want to pause the video and get that copied. Okay, while you pause the video, I switched out the paper so I can finish writing with this. My example 2 says, determine whether the relation is a function. So again, remember, it's all about the X. You don't care about the Y. Okay, I mean, if you think of graphing this stuff on the coordinate plane, if you have 2 points on the same, for the same X but different Y's, that's not going to pass the vertical line test. And so that's not a function. We can know it that way too, graphically. So it is all about the X's. So if you're determining if a relation is a function, you're going to look through the ordered pairs and just simply determine if the X values are repeated or not. So here I see that I have X is 1, that's okay. X is 3, that one's okay as well because it's not a 1. 5 is okay because it's not a 1 or a 3. And then here I see a 5 again. That's where I have to say, nope, you're done. You relation, you are not a function. Okay, one element. in the domain is repeated. And when this happens, we do not have a function. All right, on to the next relation. I've got a 1. A 3 is okay because it's not a 1. A 6 is okay because it's not a 1 or a 3. An 8 is okay because it's not a 1, it's not a 3, it's not a 6. This here is a function. We say all x values are different. Or all domain values are different. We could also say here the function is 1-to-1. Okay, so if you have questions, you know what to do. Post a comment, ask in class, come to a Google Meet. Same old, same old. All right, that takes care of the basics of functions, the beginning part of this anyway, a relation, domain and range, and how to tell if a set of ordered pairs, a relation, is a function. But we don't always just get sets of ordered pairs and look for repeated x's, especially if the set is large. Who wants to do that? Sometimes we're given the equation. All right, and this part of the section in the chapter is determining whether an equation represents a function. And functions are usually given to us in terms of equations rather than sets of ordered pairs. All right, now don't let this be difficult for you either, because it's really not that terribly difficult to determine if an equation represents a function or not. I mean, if I look at this one, okay, and I'm like, oh, well, 2x plus y equals 6. If I solve that for y, I get y equals negative 2x plus 6. Well, isn't this a y equals mx plus b? Isn't this a graph of a line with a negative slope? Passes the vertical line test for sure. So I'm going to say here that each different x will give exactly one y. Meaning, if I want to evaluate this or find the value of y for a particular value of x, if I put a 1 in here, well, negative 2 times 1 is negative 2 plus 6 is 4. So when x is 1, y is 4. If I put a different value of x in there, I'm not going to get a 4 back out. I can't. If I put a 2 in here, this is negative 4 plus 6 is 2. So then the ordered pair there would be 2, 2. And if I put a 3 in here, again, this is negative 2 times 3 is negative 6 plus 6 is 0. So the ordered pair is 3, 0. I'm not ever going to have the same x value, being paired with a different y. So each x will give exactly one y. And so we know this is a function. And really, the be-all, end-all with these problems right here is just solve the equation for y. You're going to be able to tell immediately. So solve for y. We had something similar earlier in the year that we just solved the equations for y to tell if the equation was consistent or inconsistent or dependent. I don't know if you remember that, you recall that. But the be-all end-all here is just solve for y. If you could tell right away that this thing is linear and it passes the vertical line test, you're done. This one here, this is the equation of a circle whose center is 0, 0 and radius is 1. This is a tiny circle. Now, if you recognize this to be the equation of a circle, you should also know that a circle does not pass the vertical line test. So you should also be able to conclude then, since this won't pass the vertical line test, it's not a function. All right. But I said, just solve it for y. All right, so we do y squared equals 1 subtract x squared. Take the square root to get rid of the squaring. Y equals positive, negative. Remember, when you square root to remove squaring, it's always plus or minus. 1 subtract x squared. And do you see this little thing right here? That plus or minus means the same x is paired with two different y's. So depending on the value of x, and now this is kind of like a strange one because your domain and range on the graph of this circle is not very big, right? The radius is only 1. So I'm only going from -1 to +1, okay? And so this isn't, again, a very big circle, so you don't have a lot of x values. But you could pick a half and square a half and do 1 subtract that and take the square root of it. You're going to find that when x is 1/2, you're going to get positive and a negative value for y. That's the same x being paired with two different y values. That's not a function. And it's because of this plus or minus. And this is why I say just solve for y. Because if you don't get a plus or minus, then it's a function. But if you get a plus or minus, it's not a function. Not a function. So we'll put here for every value of x, you get two y values, or two y's. And we'll do this with an indifferent face there. Okay, so for every value of x that you substitute into this equation, you're going to get two y outputs. The key here is the plus or minus. Okay, and that's what's stopping this thing from being a function. It's a circle. It doesn't pass the vertical line test. This one right here, this is square root function. Guess what? This one is a function. Right? And again, just like this one, each different x will give you exactly one y. You know, if I want to make sure that I have perfect square, if x is 5, okay, so I put a 5 in here. 5 plus 4 is 9. The square root of 9 is 3, negative. So when x is 5, y is -3. If I put a 5 in there again, I'm not going to get a different answer other than just -3, because there's no plus or minus here. This is a function, and we say that this will be 1-to-1. And if you're not already familiar with what the square root function looks like on the coordinate plane, the basic square root function is going to take on this shape. And so that itself does pass the vertical line test. Okay, so if you have any questions on determining if the equation defines y as a function of x, please post in the homework discussion. Ask a question in class. You know, the same thing that we've been doing this whole year. All right, a little bit more, and then you have a small assignment to do. Moving on, when an equation represents a function, we use function notation such as f of x, right? It's the f with the x inside the parentheses. F of x represents the value of the function at the number x. Folks, this f of x is really the y. And the y is the value of the function at that given value of x. When we're evaluating a function, you substitute the value for x into the equation of the function. Okay? In other words, here in example 1, I have an equation, a function. I know it's function because it's function notation, f of x. I also know it's a function because this is quadratic, and a quadratic is the graph of a parabola. And a parabola passes the vertical line test. So I know this is a function. So if I want to evaluate this function at a particular value of x, say like f of -5, everywhere I have an x in the given equation of the function, I'm going to replace it with a -5. As you see, f of -5 really is f of x when x is -5, right? This is f, this is the parentheses, x is -5. So if I want to know the value of the function f of x equals x squared minus 2x plus 7 when x is -5, then everywhere I have an x, I leave a parenthesis and I substitute a -5 in its place. And look, I forgot the squaring. There we go. All right. So f of x equaling x squared subtract 2x plus 7 becomes f of -5 equals -5 squared subtract 2 times -5 plus 7. All right. You should have seen this in Algebra 2. All right. Whenever you square a negative, it's always positive. Negative multiplied with a negative is positive. Add 7. And so my function value here, f of -5 is 25 plus 10, 35 plus 7 is 42. Okay, so on the graph of this parabola, when x is -5, the y value is 42. Now, this is a parabola that opens up, so my vertex is going to be a minimum point, right? Leading coefficient's positive, the parabola opens up. So, on the graph of this function, when x is -5, the y value is 42. Right? So, let's just say this was the vertex. It's not, but let's just say this was the vertex. The min or max would happen at this number x, and the value of it would be 42. So since we don't know if this is a max or a min, we just know it's a point, we're saying at -5, the value of the function is 42. Okay, so once more, you are going to set this up, and everywhere you have an x, you know, this x is going to get replaced with a -5, and so is this one. You have to replace it for each x. All right, moving on. We're going to use the same function, so let me highlight it. Because we're going to use the same function to evaluate f of x plus 4 this time. F of x plus 4. So again, I'm going to do the same thing. I'm going to write a template. Here's my x squared, subtract my 2x plus 7. I look and I make sure that I have everything, okay? There's my parenthesis for x squared, my minus 2 times x plus 7. Now I'm going to take my x plus 4 and substitute. These kind are a little bit more work because you have to square out this binomial. And if you know how to square a binomial pretty quick, you're golden, all right? Square the first, x squared. Square the second, plus 16. First time, second, then double, plus 8x. Distribute minus 2x minus 8 plus 7. Combine like terms. I only have one x squared term, so that goes there. Linears. 8 subtract 2 is 6. And then constants. 16 subtract 8 is 8 plus 7 is 15. So, on this parabola, f of x plus 4 gives us that output. Oops. Okay, so again, all I did from here I squared this out and I distributed to get this, and then I combined like terms to get that. One more. f of the opposite of x. F of the opposite of x. Again, the process is the same. You set up the template, x squared, subtract 2 times x plus 7. This is going to be important that you know how to find the f of the opposite of x, because we're going to do that when we do odd and even functions and inverses and all that stuff. Okay, negative x. When I square negative, it's positive, so that's positive x squared. This is going to be positive 2x, and this is positive 7. So f of the opposite of x equals x squared plus 2x plus 7. All right, if you have any questions on this, or you're a little fuzzy on this from when you had Algebra 2, watch the video again, post a comment for me, ask me a question. I will help you any way I can. And that is the end of this part of Chapter 2, Section 3. Have a great day.